In today's video, we're going to do a bunch of different example problems for calculating the frequency, wavelength, and period for pendulums, for water, sound, and light waves, and also for masses that are oscillating on a spring. We're going to do those in 3 separate sections. You can switch between the sections by using the chapters at the bottom of the screen. Before we get started, please don't forget to subscribe to our channel. Support our channel step-by-step science. Please subscribe, click the notifications bell so you don't miss anything, leave us a nice positive comment, give it a thumbs up, and don't forget to share this video. And in addition to that, we have made a bunch of other teaching and learning materials which you can find on our Teachers Pay Teachers store. The link, of course, is to that. For that is in the description below. Let's get started. We're going to start with some problems for pendulums. This is example number 1. It says in physics class, a student measures that it takes 14.5 seconds for a pendulum to complete 12 cycles. What is the period and frequency of the pendulum? Now, from the information that is given, you can calculate the period and the frequency using kind of the definition of period and frequency. Period is the time it takes for one cycle, and frequency is a number of cycles per unit of time, which is the second. So in this problem, we've been given the time, 14.5 seconds, and the number of cycles, 12, so we can easily calculate the period as 14.5 seconds divided by 12 cycles, and that means that the period, the time for one cycle, is 1.2 seconds. The frequency is just the inverse of that. It's the number of cycles in the unit of time, so 12 divided by 14.5 seconds. You get the frequency is 0.83 hertz, or 0.83 cycles per second. Now, you can also use the relationship that we just said, that the frequency and the period are inversely proportional. So we just check our value for the frequency by using this equation and plugging the period in. This shows that the frequency and the period are inversely proportional to each other. So the frequency is just going to be 1 over the period, and we should get the same frequency, and we do. And that shows us that we probably did that correctly. That's example number 1. Example number 2 is now we're going to use the equation for the period of a pendulum. It says, what is the period and frequency of a simple pendulum that has a length of 1.1 meters? Now, in this problem, you can see we're not given the number of cycles or the time or anything like that. We're just given the length. So this is the equation we're going to use. It's the period is equal to 2 pi, then the square root of the length divided by g. And now it doesn't say this, but we'll assume we're on Earth, so g is going to be 9.81. All we got to do is simply plug the values in. So that's the period is 2 times pi times the square root of 1.1 meters over 9.81 meters per second squared. That gives us that value, and if we complete that calculation, we get that the period is 2.10 seconds. Now we're also asked for the frequency, and again, we can use the relationship that the frequency and the period are inversely proportional. That means the frequency is 1 over the period simply. That's just 1 divided by 2.10 seconds, and you get that the frequency in this case is 0.48 hertz. That's half a cycle per second. Okay? Number 2. Now for number 3, we're going to use the same equation, but now we've been given the mass, okay, and has a period, and we want to know what is the length of the pendulum. Okay, what is the length of the pendulum? So now in this case, we want to solve this equation for L. Okay, we know the period, we know G, we've been given the mass. And that's not to throw you up, but that's just to remind you that in this equation for the period of the pendulum, the mass is not important. The period is not dependent upon the mass, so we need to leave that out. We're not going to use that, but we want to solve for the length, and we're going to do that first by squaring both sides of the equation. If we square both sides of the equation, on the left-hand side we get t squared. On the right-hand side, we get the whole term. You got to square the whole term like that. And then you get that it's t squared is equal to, now this square and this square root are going to cancel with each other. So on the right-hand side, we're left with 2 pi squared times L. Okay, but we got to square the 2, which gives us 4. We got to square pi, which gives us pi squared. And since the L was under the square root sign, we're just left with L divided by G. Now we want to solve for L. So that means we're going to multiply both sides of the equation by g. Then we get on the left-hand side t squared times g equals, the g's are going to cancel, 4 pi squared L. Then we're going to divide by 4 pi squared, and we're left with L, the length of the pendulum, is equal to the period squared times G divided by 4 pi squared. So that's the equation which we'll bring over to the other side of our slide here, the next slide. And now we can plug the values in because we know the period is 1.15 seconds. We said we're on Earth at G. 4 is 4, and pi squared is pi squared. And we just plug those values into the equation. We get the length of that pendulum would be 0.33 meters. So a pendulum that has a period of 1.15 seconds must be 0.33 meters. Okay? That is solving for L. Now, we don't necessarily go off that often to an unknown planet in the solar system, but let's just see if we can calculate G. Okay, in this case, we want to calculate G. We want to know what's the acceleration due to gravity on the planet and what planet are we on. You are on an unknown planet. Your pendulum has this length, and it completes 8 cycles in 12 seconds. We want to know what is the acceleration due to gravity and what planet could we be on. Now, we need the period first. You can see we're given cycles in seconds, so the first thing we have to do is calculate the period. By definition, the period is the time per cycle. So we're going to take 12 seconds divided by 8, and the period is 1.5 seconds. Okay, now we're going to do that on the next slide here. Here's the period we calculated on the previous slide. We want to solve for G, so we're going to do the same thing. We're going to square both sides. Once again, we get t squared. And then the squared here is going to cancel with the square root. So we're going to square the whole thing, which means we're going to get 4 pi squared over L divided by G. Okay? This squared cancels with the square root sign. But we've got to remember to square the 2 and the pi. 4 pi squared L over G. Now, you know, and I know that if we have a fraction on the right-hand side and a single value over here on the left, we can just switch these two values. That means that G is going to be equal to 4 pi squared L divided by t squared, the period squared. And if we plug the values in, we get a value just about 11.4 meters per second squared. Now, is there a planet in the solar system that has that acceleration due to gravity, that gravitational field strength? Well, we can look at a table, and you can see that we would be here probably on Neptune, like that. There's Neptune. And now, of course, Neptune is a gaseous planet, so you can't really be on the surface of Neptune. But if you could, that would be the acceleration due to gravity, and that's what your pendulum would be doing on Neptune. Okay, so that is the problems, or those are the problems for the pendulum 1 through 4. And now we're going to go through and calculate frequency, period, wavelength, and velocity for sound, light, and water waves. And for number 5, this is fascinating. Humpback whale songs have a range of frequencies from 20 hertz all the way up to 24,000 hertz. That's pretty big. And if a song has a frequency, the sound has a frequency from a whale of 35 hertz. What's its wave? And the wavelength is 44 meters. What's the speed of that sound? Okay, the whale song from that sound wave. So we can simply use this equation. This is kind of many people refer to this as the wave equation. The velocity is equal to the frequency times the wavelength. This is the Greek letter lambda. The Greek letter lambda is used for the abbreviation for the wavelength. So we're given the frequency, 35 hertz. We're given the wavelength, and we can plug those values in, and you simply get that the speed of that wave is 1,540 meters per second. And that is generally approximately what we would consider the speed of sound in water, especially seawater. Because as you know, whales don't live in air, they're underwater. And that would be the speed of sound in water. Okay? So that is the velocity of that wave, which has that frequency and that wavelength. Okay, the next one is about elephants. Elephants use very low frequency sound to communicate with each other. Okay, now this is generally accepted at approximately 340, 345, the speed of sound in air. We want to know what is the wavelength if the frequency is 15 hertz. That's below what humans can hear. All right, and now we're going to use the same equation. This is the wave equation. Velocity is the frequency times the wavelength. Now we want to know, okay, what is the wavelength in this case? So we're going to now solve for the wavelength. And if we do that, we're going to divide both sides by the frequency and get the wavelength is equal to the velocity divided by the frequency. The velocity we were told is 345 meters per second. The frequency we were told was 15, and that means that the wavelength of that wave is 23 meters. Okay, so that was one for sound in water, and that is sound in air. And now the next one we're going to do is to talk about bats. These are all animals who use echolocation to find things. To navigate, to find its way around, and to find insects to eat, bats emit a high-pitched sound that has a wavelength of 22.5 millimeters. This is millimeters. The speed of sound in air, okay, when the previous one we said 345, but depending on the temperature, we're going to say this time it's 340 meters per second. We want to know what is the frequency. Okay, so we're going to start with the same equation. Velocity is the frequency times the wavelength. We want to solve for the frequency. Now we're going to divide both sides by the wavelength. And that means the frequency is the velocity divided by the wavelength. The velocity is 340 meters per second. The frequency now, the wavelength is 22.5 millimeters. So I put times 10 to the minus 3 meters. We have to convert this millimeters into meters, so that'll cancel with this meter. And then we get the frequency is 15,101 hertz, which we could write and approximate as 15,000 kilohertz. Okay, that's the frequency of that sound from some insect, or from the bats that you use to find insects. Okay? Okay. Now, I think the last one for this section is we have sunlight. In sunlight, the sun emits a broad spectrum of light all across the electromagnetic spectrum. But let's just say it's going to emit some yellow light. This yellow light has a frequency of 1.6 times 10 to the 14 hertz. And we want to know what is the wavelength. Okay, it doesn't actually left it out here. What is the wavelength of this yellow light? Okay, so you'd say, what is the wavelength of this yellow light? Now, we're going to use the same equation, but instead of writing V, we write C, because C is a constant. It's the speed of light. And the speed of light in a vacuum, when the sun is shining, there's basically a vacuum between here and the Earth, between the sun and the Earth. We put C in here, but this is the same equation. But we put C because we know that the speed of light in a vacuum is approximately 3.0 times 10 to the 8th meters per second. So we're solving for wavelength again, so it's C divided by F. I gave you, or you're given the frequency as 1.6 times 10 to the 14 hertz. You divide those two values, the speed of light divided by the frequency, and you get that is 5.81 times 10 to the minus 7. Okay, this should be meters here, not meters per second, of course. This should be meters. And then that would give us a wavelength of 581 nanometers. Okay, that's the color, approximate color of yellow light. All right? Okay, so now we've done the pendulum problems, and now we've done the water, sound, and light wave problems, and now we're going to do the mass oscillating on a spring. Okay, and so number 9 says here, in a physics class, a student measured that it takes 18.1 seconds for an oscillating spring to complete 20 cycles. We want to know what is the period and frequency of the spring. Okay, the spring would have a mass on the end of it, and that mass would be oscillating. Now we're going to do the same things we did for the beginning for the pendulum problems. We're given the frequency, we're given the cycles and the time, the number of cycles and the time. So we can use the definition for the period, time per cycle, and the frequency, number of cycles per unit of time. And we can plug those values in, 18.1, and that divided by 20 gives us that the period is going to be 0.91 seconds, the time for one cycle. And then the frequency is 20 divided by 18.1, and that means 1.10 cycles per second, or 1.10 hertz. All right, number 9. Now we can do the same thing and confirm the frequency using this equation, also this relationship. See if we get the same answer. Okay, number 10. It says, what is the period and frequency of an oscillating spring that has a spring constant of 10 Newton meters, and the mass attached to it is a 200 gram mass? So here's the equation that we use. Looks similar to the pendulum one, but it says the period is equal to 2 pi. Now this is the mass divided by the spring constant, the square root of the mass divided by the spring constant. And you can see we have the mass, and the mass we have to convert into kilograms, so it's 0.200 kilograms divided by 10, and you get that the period would be 0.89 seconds. And again, the frequency, we can use this frequency equation, that the frequency and the period inversely proportional. The frequency is 1 over the period, and that means that the frequency is 1.3 hertz or 1.3 cycles per second. Okay, so there you go. The next one, it's going to be similar. We have a child in a bouncy swing. It's suspended by a spring. If the spring stretches 15 centimeters when there's an 8.5 kilogram child put in it, what is the spring constant and how much time does it take for the child to complete one cycle? So you can see in this one, we're not given the spring constant. So we got to calculate the spring constant. This is the equation we use to calculate the spring constant, that the force on the spring is equal to minus K, the spring constant, times the extension of the spring. And this minus sign just tells us that this force is opposite of this one. Okay, the spring pulls up, the object pulls down, pulls in different directions. We're going to calculate K. The K is going to be the force divided by the extension. Now we're given the mass, so you got to multiply that by 9.81 to get the force. Divided by x, the distance, and it says 15 centimeters, that's 0.15 meters. We get the spring constant, it's just about 556 newtons per meter. Kilogram meter per second squared is a newton divided by meters. Now we can use our equation to calculate the time. All right? So once again, we're given the kilograms, the mass, and we calculated the spring constant, and that gives us and tells us that the period for that spring, that bouncing child, would be 0.78 seconds. All right. The next one says an object at the end of the spring oscillates with a frequency. So we're given the frequency, and we're given the spring constant. Now, we're going to use this equation, but we're not given the period, so we're going to have to calculate the period first. All right, but we're going to start off by, we want to solve for m. So we're going to do the same thing we did with the pendulum problems. We're going to square both sides. And when we square both sides, we get t squared, and that's going to be equal to 4 pi squared m over k. All right, and we are going to solve this equation for the mass. So we're going to first multiply both sides by k. Then we're going to cancel those, and we get that. And we want to solve for m, so we're going to divide both sides by 4 pi squared. And we get the m equals t squared times k divided by 4 pi squared. We're given the spring constant here. Okay, we want to solve for the mass. So on the next slide, we can just plug the values in. Okay, now like I said before, we weren't given the period. We were given the frequency here. So we got to get the period also first. And that means it's 1 over the frequency. And the period is 0.31 seconds. So we can plug those values in now. 0.31 squared times the spring constant of 180 divided by 4 pi squared. And we get the mass, okay, of that object is 0.44 kilograms or 440 grams. Okay, we got one more spring problem, and in this one, it says an object at the end of a spring oscillates with a period of 1.85 seconds. The mass of the object that's on the end of the spring has a mass of 1.5 kilograms, and in this case, we want to know what is the spring constant. So we're going to do the same thing again. Square both sides, t squared, cancel. We get 4 pi squared over m divided by k. We want to solve for the spring constant, so we can just switch these two as we did before. And then you get k equals, the spring constant equals 4 pi squared over m divided by t squared. Take that over to our next slide. Plug the values in. 4 pi squared, the mass is 1.5 kilograms. The period is 1.85 seconds. We square that. And you get the spring constant is 17.3 Newton meters, which means it takes 17.3 newtons of force to stretch that spring 1 meter, newtons per meter. Okay, we're going to end up, I thought we'd do one more pendulum problem. What is the period of a simple pendulum that has a length of 75 centimeters? So once again, we're just going to use this equation. Remember, this is the period of the pendulum. And we'll put the values in the length. We got to convert to meters. We're going to assume we're on Earth, 9.81. And therefore, you get, in that case, that the period of that pendulum, that's 75 centimeters long, is 1.74 seconds. Okay, so there you go. We did 14 different example problems for oscillating objects, pendulums, light, sound, and water waves, and masses that are oscillating on a spring. I hope you found the video helpful for that variety of problems. If you did, please do all of the following 5 things. Please subscribe to our channel, support our channel, Step-by-Step Science. Give us a thumbs up, leave us a nice positive comment, share, don't forget to share, and click the notifications bell so you don't miss anything. Thank you so much for watching. We appreciate it very much. We'll see you in the next video.